What if we could create a model of Earth as small as a postage stamp, the tip of a pin, or even the size of a single atom? Miniaturization, a core aspect of modern technology, makes this idea possible through advances in nanotechnology, atomic manipulation, and quantum physics. A postage stamp-sized globe could be crafted using microscale engineering, etching continents and mountains with precision tools like micro-electromechanical systems. This miniature model might be used for compact data storage, advanced mapping, or even environmental monitoring. Shrinking further to the size of a pin tip, nanotechnology could etch Earth's features onto materials at the molecular scale, using techniques like nanoscale lithography. For example, a scanning tunneling microscope might carve out intricate patterns invisible to the naked eye, similar to painting the Mona Lisa on a needle's head. At the atomic scale, the globe would blur the lines of physical representation, existing as a quantum object where geographic features are represented by individual atoms. These miniaturized globes could revolutionize science and education, enabling breakthroughs in data storage, climate simulation, and quantum mechanics, while showcasing the incredible potential of human ingenuity. The miniaturized globes could revolutionize the changes in the way we think. What if scientists could create a model of Earth scaled down to the size of a postage stamp, the tip of a pin, or even a single atom? Miniaturization, a cornerstone of modern technology, has enabled devices to become smaller, faster, and more efficient. Achieving such feats would require groundbreaking advancements in nanotechnology, atomic manipulation, and quantum physics. Each scale introduces unique challenges and opportunities, from preserving complex details to exploring physical properties at the quantum level. Such efforts could revolutionize data storage, simulation, and even our understanding of the universe. Nanoscale 3D printing could theoretically create a globe the size of a pin tip using advanced lithography techniques to etch continents and oceans with atomic precision. A triumph of scientific ingenuity. A globe scaled to the size of a postage stamp could be realized through microscale engineering. Technologies like micro-electromechanical systems might etch intricate details such as continents and mountain ranges onto the surface. These mini globes could serve as educational tools or data visualization devices, with potential applications in compact data storage and advanced mapping for drones and autonomous vehicles. Can a postage stamp sized globe might even integrate sensors for environmental monitoring, encoding data about global temperature changes or ocean currents. This innovation would resemble a high-resolution snapshot of Earth condensed into a pocket-sized marvel. A globe reduced to the size of a pin tip presents even greater challenges. Nanotechnology would be required to manipulate materials at the molecular or atomic level. Techniques like molecular self-assembly or nanoscale lithography could preserve details like topography and geographic features, though these would be smaller than the wavelength of visible light, making them invisible to the naked eye. Using scanning tunneling microscopes, STMs, scientists could etch nanoscale patterns representing Earth's continents onto a single crystal of silicon, creating an almost invisible globe. Such precision would be comparable to painting the Mona Lisa on the head of a needle. Scaling down further to the size of an atom pushes the boundaries of quantum physics. At this level, classical physics breaks down and quantum effects dominate. A globe of this scale might exist as a quantum object, governed by wave-particle duality, superposition, and uncertainty. Physicists could use individual atoms to represent Earth's geographic features, arranging them with atomic force microscopes. AFMs. This atomic scale model could serve as an experimental platform for testing theories in quantum mechanics. Miniaturizing a globe across these scales introduces numerous challenges. At the microscale, advanced tools like femtosecond lasers or electron beams would be needed. At the nanoscale, atomic vibrations and thermal fluctuations would complicate precision. At the quantum scale, maintaining structural integrity becomes difficult due to the unpredictable nature of particles. Overcoming these challenges requires interdisciplinary advancements in physics, engineering, and material science. Ah, huh. For instance, thermal expansion at the nanoscale could distort a globe's features, necessitating cryogenic stabilization. These challenges are similar to building a skyscraper out of sand grains, requiring exceptional ingenuity to ensure stability and detail. Miniature globes at these scales could have profound scientific and educational impacts. A microscale globe might simulate climate patterns on compact surfaces, while a nanoscale globe could revolutionize data storage by encoding information in physical form. At the atomic scale, such a model could study quantum interactions and chemistry. These globes would not merely represent Earth, but act as platforms for groundbreaking discoveries, akin to compact encyclopedias holding vast amounts of information. Miniaturizing to the atomic scale raises philosophical questions about representation and scale. At what point does a model of Earth cease to resemble the original and become an abstraction? Details blur into statistical probabilities and quantum uncertainties, challenging our understanding of replication and reality. At the atomic level, the globe might only exist as a mathematical construct rather than a tangible object, redefining the boundaries of comprehension. Creating these globes requires advancements in nanotechnology, quantum computing, and material science. Tools like atomic force microscopes, femtosecond lasers, and quantum dots are essential for achieving precision at the nanoscale. Computational modeling and AI algorithms will also play crucial roles in designing and optimizing such structures. Each technological breakthrough in this area could lead to broader applications in medicine, computing, and energy storage. AI-assisted nanolithography, for example, could fabricate nanoscale globes with previously unattainable precision. Beyond their novelty, miniature globes open doors to futuristic applications. Nanoscale globes could act as ultra-dense data storage devices or prototypes for planetary simulations. At the quantum level, they might test theories about the fundamental nature of matter and energy. These globes could even encode humanity's knowledge base for interstellar communication, compressed into an indestructible format suitable for space travel. Creating a globe scaled to the size of a postage stamp, pin tip, or atom is more than a scientific challenge. It is a profound exploration of technology, representation, and imagination. Each scale offers unique opportunities for innovation, advancing data storage, simulation, and our understanding of quantum reality. These marvels of engineering would redefine our perception of the universe and expand the boundaries of human ingenuity.